As mentioned in the previous video, there are other techniques of numerical integration that will provide a more accurate estimate of the area using the same or smaller number of subintervals. The left, right, and midpoint rules are all based on using rectangles to estimate the area. And this comes from the fact that rectangles are the easiest shape to find the area of because they have the simplest formula, length times width. However, they do not necessarily provide the most accurate estimate because the nature of a curve is that it is not flat. Most curves are not flat. Most of them are sloped to some degree or another. So using a flat line, a horizontal line at the top of the subinterval is not necessarily going to give the best estimate. What might seem like a more intuitive estimate would be to use a slanted line at the top of the subinterval. So let's look at an example of a curve. We'll use a similar one to what we saw in the previous video. And again, we will, just to make it easy here, to make it doable on the size of this graph, we will split it into 4 subintervals. Now, the idea here is that, like with the rectangles, like with the midpoint rule, we're going to have a shape that sits flat on the axis, which makes sense because that is the bottom of the region we're looking for. Now, with the midpoint rule, we would calculate the midpoint of this subinterval, use the y value at that midpoint to draw a horizontal line. But that is not going to give the best estimate of the region because, as we saw when we did this, a horizontal line across this is going to result in a shape that excludes a portion of area up here that it should include, and includes a portion of area here that should not be included. Now, fortunately, those two regions tend to roughly balance each other out. But what if we decided to draw this shape a little bit differently? What if instead of using a rectangle, instead of using a horizontal line, what if we went to the y value at each endpoint of the interval and connected them with a diagonal line? Now, while this is still going to give a little bit of an overestimation, it is very, very, very close to the actual shape of the curve. The idea being that because the curve does have some slope to it, that using a sloped line instead of a horizontal line will be a better approximation of the actual shape of the curve. We repeat this procedure on each subinterval. Now again, depending on the concavity of the curve here, we may find that the trapezoid rule overestimates or underestimates. However, I think we can agree that the shape traced by each of those diagonal line segments is definitely a better approximation of the actual shape of the curve than a series of horizontal line segments would do. So the idea here is to use trapezoids, which is what each of these shapes are. Each shape has 2 parallel sides, these vertical lines at the left and right endpoints of the subinterval. And then connecting the endpoints of those 2 parallel lines are other line segments. That is the definition of a trapezoid. The area of a trapezoid is given by the formula 1/2 times the sum of the lengths of the two parallel sides, which usually when we're looking at a trapezoid that is oriented horizontally, we would call them bases. So 1/2 times b sub 1 plus b sub 2 is actually the average lengths of the bases. And then that is going to be multiplied by the height, the distance between those two parallel sides. In terms of the function and the trapezoids drawn in the function, the area of the ith trapezoid would be 1/2 times the sum of the two parallel sides. The two parallel sides are the y value at the left endpoint and the y value at the right endpoint. And the distance between them is delta x. This would be the area of the ith trapezoid. So that, for example, if we were using the 4 subintervals we have up here, the area of this region would be approximated by 1/2 times f of x sub 0 plus f of x sub 1 times delta x plus 1/2 times f of x sub 1 plus f of x sub 2 times delta x plus 1/2 times f of x sub 2 plus f of x sub 3 times delta x plus 1/2 times f of x sub 3 plus f of x sub 4 times delta x. A little bit of algebra here will allow us to simplify this so that it doesn't look quite so horrifying, because admittedly at the moment it does look rather intimidating. This looks far more complicated than the midpoint rule did. But a little bit of algebra will allow us to simplify this so that it's actually not bad at all. First off, every one of these has a times 1/2, which means we can factor that out. Likewise, every one of them has a delta x, which can also be factored out. I'm going to actually put the delta x in front with the 1/2 for reasons we'll see in a moment. What we have then is, from the first trapezoid, we have f of x sub 0 plus f of x sub 1. And then from the second trapezoid, we have f of x sub 1 plus f of x sub 2. From the third trapezoid, we have f of x sub 2 plus f of x sub 3. And then from the fourth trapezoid, we have f of x sub 3 plus f of x sub 4. The idea here is that we can combine some like terms because we have f of x sub 1 giving us the right side vertical line of the first trapezoid, and then also f of x sub 1 being the left side vertical line of the second trapezoid. Likewise, f of x sub 2 is the right endpoint of the second trapezoid as well as the left endpoint of the third. F of x sub 3 is the right endpoint of the third as well as the left endpoint of the fourth. So each interior x sub I is overlapped because it serves as both the right endpoint of one trapezoid as well as the left endpoint of the next. The only two that don't get doubled is the very first left endpoint and the very last right endpoint. So that this can be simplified. I'll come back to the 1/2 and the delta x in a moment. This can be simplified as f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3 plus f of x sub 4. In this way, every interior x sub I is used twice and therefore has a coefficient of 2. The very first x sub 0 is only used once because there is no trapezoid on both sides of it. There's only a trapezoid to the one side. Likewise, at the very end of this, at x sub 4, we again only use that side once because there is no second trapezoid on the other side of it. Now, as for the 1/2 and the delta x, in this case, is going to be given by the distance between the right endpoint of the interval and the left endpoint of the interval divided by however many subintervals there are, which in this case is 4. We now need to generalize this. This is specifically the trapezoid rule for 4 subintervals. We need to then generalize it for n subintervals. So we're going to start, as usual, with a function that must be continuous in order to be integrated. The area, then, of the region bound by the graph of f of x and the x-axis on the interval in question can be approximated using a series of n trapezoids. And the area is approximated by the formula 1/2 times b minus a over n. This is often then written as b minus a over 2n times f of x sub 0 once plus f of x sub 1 twice plus f of x sub 2 twice, etc. up to the next to last endpoint, f of x sub n minus 1, which also gets used twice, and then lastly, the last endpoint, which only is used once. This is the trapezoid rule, which honestly is really not much more difficult than the midpoint rule. In fact, it might even be considered a little bit easier because we don't have to calculate the midpoint first of all. We can just use the left and right endpoints directly. And really, all that's introduced that's new is the 1/2 in front of the delta x and the 2's as coefficients in front of all of the interior y values. Otherwise, this actually isn't bad at all. So let's test it out using the same example that we used for the midpoint rule. We're going to use f of x equals sine of x on 0 to pi, which we know from having looked at this in a previous video, that the actual area given by the integral from 0 to pi of sine of x dx, the actual area of this actually is 2. So keeping this in mind, we'll now be able to look at the estimates given by the trapezoid rule and see if they're even close. So, first of all, we're going to use the trapezoid rule with n equals 4 subintervals. So our x sub i's are going to be 0, and then pi over 4, and then pi over 2, and then 3 pi over 4, and then pi itself. So our area by the trapezoid rule is going to be approximated by b minus a, the full width of our interval, divided by 2 times the number of subintervals. That's our 1/2 times delta x. And this is going to be multiplied then by sine of 0 plus 2 times sine of pi over 4 plus 2 times sine of pi over 2 plus 2 times sine of 3 pi over 4 plus 1 times sine of pi. And the rest of this is just evaluating it. Now again, eventually we're going to have to put this into the calculator, but a little bit of evaluation now or algebra will help us to simplify what we have to put into the calculator. So for example, we can simplify the fraction out in front to be pi over 8. We also know then that sine of 0 is equal to 0. Likewise, sine of pi is also equal to 0. So we really only have to worry about the 3 terms in the middle. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 2 is 1. The sine of 3 pi over 4 is again the square root of 2 over 2. And the sine of pi is, as mentioned before, 0. Again, a little bit of simplification can help here, so that we end up with the square root of 2, and then another square root of 2, giving us together 2 times the square root of 2. And then 2 times 1, of course, is 2. And this is quick and easy to put into our calculator. And when we do, this will give us approximately 1.896. Not the greatest estimate, but not too far off either. It is a little bit lower than we might expect, and if you want to draw the graph of this function, we would see that because of its concavity, that the trapezoids will always be an underestimation. Thus, we get an area that is smaller than the actual area. Like with the midpoint rule, we're going to do this again, this time using 8 rectangles, or I'm sorry, 8 trapezoids, to show that by using more, we get a better estimate. At the same time, it is not going to get terribly much more complex. So first of all, our delta x is going to be pi minus 0, this time divided into 8 subintervals. So our delta x is going to be pi over 8. This makes our x sub i's 0, and then pi over 8, and then 2 pi over 8, or pi over 4, and then 3 pi over 8, etc., 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8, and lastly, 8 pi over 8. So that our area will be approximated by pi minus 0 over 2 times 8 times sine of 0 plus 2 times the sine of pi over 8 plus 2 times the sine of pi over 4 plus 2 times the sine of 3 pi over 8 plus 2 times the sine of pi over 2 plus 2 times the sine of 5 pi over 8 plus 2 times the sine of 3 pi over 4 plus 2 times the sine of 7 pi over 8, and lastly, 1 times the sine of pi. And again, this might seem dramatically large. However, we do know a few things from having dealt with this in the previous example with n equals 4. Fortunately, and this is not always the case when we switch n's, but fortunately, a lot of these x sub i's are the same as we saw in the previous example. So what we can do is take the 3 terms that we saw in the previous example, because we already know what those 3 terms evaluate to. Of course, the sine of 0 and the sine of pi are both 0, so they do not figure into this at all. So we have in front pi over 16. The 3 highlighted terms we know are going to come out to be 2 times the square root of 2 plus 2. And then we have 2 times the sine of pi over 8 plus 2 times the sine, 2 times the sine of 3 pi over 8 plus 2 times the sine of 5 pi over 8 plus 2 times the sine of 7 pi over 8. As we saw with the midpoint rule, though, we know that some of these are symmetric to each other. Pi over 8 is symmetric to 7 pi over 8 in that they have the same y-coordinate. So these two things together can be combined to be 4 times sine of pi over 8. And again, at this point, this is just a matter of simplifying what we're going to write into the calculator. Likewise, 3 pi over 8 and 5 pi over 8 are symmetric in that they have the same y-coordinate again. So those two terms can be combined to give us 4 times sine of 3 pi over 8. And we can put this into our calculator, which is about as simple as we're going to get it to be. And this is going to come out to be approximately 1.974. Better than the previous estimate. Still a little bit of an underestimation, but better than the previous estimate. Now, comparing this with the midpoint rule, these estimates are not quite as accurate for this particular example. In general, however, the trapezoid rule does tend to converge to approach the actual value of the area faster than the midpoint rule does. For a smaller number of n, it may not be as accurate all the time, but it certainly does approach if we were to continue on to n equals 50 and n equals 60. I'm sorry, n equals 100 and n equals 1000. We would find that the trapezoid rule will approach the actual area of 2 much more quickly. That is to say, it will become more clear that it is approaching 2 with a smaller value for n than the midpoint rule would.